Hello guys, welcome back to TechDose, and in this video we will see the shortest subarray with sum greater than equals k problem, which is from LeetCode number 862. A prerequisite before watching the current video is to watch my video on LeetCode number 209, because the technique being used here is used in this problem as well. Minimum size subarray sum. Okay, so I hope you have seen this video, and I will assume that you have seen my video on LeetCode number 209 throughout the explanation. Before looking at the problem statement, I would like to announce about our data structures and algorithms program, which is a guaranteed 3 months upskilling mentorship program, and it is highly focused for interview. So all the interview topics will be covered in 3 months along with the assignments as well as live discussions. So if you are interested to know more, then you can WhatsApp us on the given number. Now let us look at the problem statement. Now in this problem, given an integer array nums and an integer k, return the length of the shortest non-empty subarray of nums with the sum of at least k. If there is no such subarray, then you need to return -1. A subarray is a contiguous part of an array. Okay, I hope you understand this. So let us look at an example for some better understanding. Now in this case, in this example, I have taken 0 to 5, which is 6 elements, and there can be multiple windows where the sum is actually greater than equals to my k value, which is the target value. Okay, now in this case the target value is 12. I have drawn only 2 windows which are of smaller size, and there can be other windows which will be having sum greater than equals to target. Okay, now in the first window the sum is 12, which is obviously greater than equals to target, and the window size is 3. In the second window you can see that the sum value is 14, which is again greater than equals to target, and the window size is 2. Now out of all possible windows where the sum inside the window for all the elements, if it is greater than equals to target, you have to consider it and take the minimum of all the window sizes, and that will be returned as an answer. In this case, let's say you have just 2 windows, then we will take the minimum of 3, 2, and then we will get the answer as 2. I hope you understood this. Now one thing to note is window and subarray has same meaning. Both are contiguous part of the same array, right? Our goal here is to find the minimum window size which has sum greater than equals to target. So let's look at the sliding window technique, which I had explained in LeetCode number 209, which is a prerequisite of this video, and I hope you have seen that. So in that video I had explained that you can use 2-pointer technique and use the variable size sliding window in order to find the minimum window size which will have sum greater than equals to a value target. Okay, and in that video I had mentioned that you cannot do it if the elements can be negative. You may or may not get the correct answer using that technique. Now in this case I have taken an example with 6 elements. If I draw the cumulative sum graph, this is a cumulative sum graph. So if I take the first element, I'll have 2. If I add the second element to the previous element, I get 9. If I add 3 to 9, then I get 12, and so on, right? So this is a cumulative sum graph. If you look at the graph and compare it with the graph which I had drawn in the problem number 209, then in 209 I had explained that the graph will be monotonically increasing. But in this case, this graph is not monotonically increasing. Okay, in this case it is also decreasing, and the decreasing curve is created because of the negative numbers. Fine. Now if you have negative numbers, then actually you cannot apply your sliding window technique using 2-pointer. So let us see for this example if that technique works. Now that technique works using a left pointer as well as a right pointer. Okay, and using a current sum value. So let's say the current sum is 2 initially. Now as soon as the current sum reaches to our target or exceeds target, then we will stop and we will move our left pointer to the right. But it is still less than the target, so I'll keep moving the right pointer. I'll add 7 to it and this becomes 9. Now I will add 3 to it and this becomes 12. Now you see that your value here is actually exceeding the target value, so yes, your right pointer will stop here. But this may not be the smallest window possible, so in the previous problem I had explained that you will compress from the left side and the left pointer will move to the right, and you will keep on moving it unless your current sum value actually decreases and becomes less than your target. So if you move your left pointer to the right, then this 2 will be decremented and this becomes 10. Now the current sum has actually fallen below your target, so you will stop your left pointer here, and this will be your window. Along with that, you also include the previous element. Okay, so you have to do r minus l plus 1 and plus 1 to this, which I had already explained in the previous video. So it will give you a window size of 3. So let's maintain a shortest window size, which will actually be containing the minimum window size with sum greater than equals to target. Initially I will give it a max value, which is basically our infinity value, and then I will try to minimize it because 3 is less than infinity. Fine. Now once this is done, we will keep on moving the right pointer to the right unless again the sum exceeds our target. So when r reaches to this minus 8, then the sum will fall to 2. Now when it reaches to 4, the sum reaches 6, and when it reaches to 10, then the sum reaches 16. Again, 16 is greater than equals to target, so our right pointer will stop at index 5. Now this may not be the optimal window size, may not be the minimum window size, so we will compress the left pointer from left to right. So while compressing, we move the left pointer one position to the right, and then we will subtract this 7. So if I subtract this 7, it comes to 9. And now 9 is less than equals to your target, so the current window will be the optimal window according to the sliding window technique. Along with that, you have to include the previous element as well. So how many elements are here? You have 5 elements. So the window size is 5. Now 5 is greater than this 3, so it will not get updated. And now again you move the right pointer to the right and you will stop because all the elements have been passed by the right pointer. Now 3 is given as your answer if you apply the sliding window technique using 2 pointers. Okay, but you will see that this example has 2 as answer, because if you take only these 2 elements 4 and 10, then you will have a sum value which is 14, and this is greater than equals to your target, and this window just has 2 elements. So obviously 3 is not the answer, right? So you have to remember that whenever the graph is monotonically increasing, then you can apply your sliding window using 2 pointers. But when the graph cannot be guaranteed to be monotonically increasing, this happens due to the negative numbers, right? Then you cannot apply the sliding window technique. You can take more examples and you will come to an understanding. Okay. Now what are our requirements in this case? Let's say that the graph was monotonically increasing, then I could have applied my 2 pointer technique to solve it. Okay, so if we can maintain a monotonically increasing curve, then we will solve it easily by using the 2 pointer techniques. Now when we find a window with sum greater than equals to target, then we minimize the window size by compressing from the left side, and this technique is the same which I had explained in LeetCode number 209 in the previous video. Okay, now this is an observation, may not be required here, but just I have written it for simplicity, that no 2 subarrays can be of minimum size where the sum is greater than equals to target and starting at the same index. So if I say that what are the subarrays starting at this 1, the subarrays will be 1 5, 1 5 3, which is starting at this 1. Now both the subarrays has sum greater than equals to target. So this is sum 6 and this is sum 9. But then there will be only one window of minimum size starting from any index. Okay, I think this makes sense. And if it doesn't make sense, then you can just leave out this point 3. It is not very important. Now, what will be the choice of data structure for solving this problem? The simple thing which comes to mind is stack, because we are talking about maintaining monotonically increasing values, and you know that monotonic stack can do that job of maintaining the monotonically increasing value, right? So this can perfectly do it, because you take a stack and you keep on inserting element as long as the elements are increasing, and as soon as you find a lower value number, then you pop out the elements unless the stack is empty, or you find a lower value number and you push the new element above it. Okay, this is how monotonic stack actually works and maintains a monotonically increasing value. Now the second requirement is compression of the window from the left. Okay, so compression of the window means there were 2 pointers. So one pointer was right, which was moving to the right, was parsing the array, and as soon as you find a sum value greater than equals to target, you had a left pointer which was actually compressing. Compressing means you have to remove certain elements from the left side. Now if you look at the stack, the insertion as well as deletion can only be done from the top end, only one end. You cannot do insertion and deletion from both the ends. So this operation will not be supported by our stack. So we have to choose another data structure, and you will see that DQ is a more powerful data structure. DQ can do all the jobs which the stack can do, and it can do even more, because in a doubly ended queue you can insert and delete from both the ends. So a DQ can maintain a monotonically increasing value, as well as we can do push and pop from both the ends, either in the beginning or at the end. So both these operations will be supported by a DQ but cannot be supported by a stack, and that's why we will pick DQ and not a stack. Okay. Now what are the DQ operations which we will be doing? Insertion of the new sum value at the end to maintain a monotonically increasing curve as we keep on parsing the array. And the second thing is, whenever we find a window with a sum value greater than equals to target, then try to pop out the elements from the left side in order to compress, in order to minimize the window size. Okay, these were the two requirements, and it can be supported by your DQ. So let us look at a dry run about how we will actually solve it. Okay. Now I have taken the same example. So in this case, I will start my parsing from this index 0. Now as soon as I see index 0, I will increment my sum value, and this becomes 2. Now I will compare this 2 with the target. Is it greater? No, it is not greater. Fine. So we will not do anything. Now we will have to push it into the DQ. The DQ is empty, right? So we have to push it into the DQ. So the DQ node will be value comma index. So value is your cumulative sum value. Okay, so what is the cumulative sum here? It is 2. So 2 comma index is 0. So this will be inserted into your DQ. Move on to the next element, and the sum becomes 7 plus 2, which is 9. Now is 9 greater than your target? No, it is not greater than your target. Now the next thing you can do is you can compare with the first element of the DQ, so that whatever is a sub array, you can find what is the sub array sum basically, right? But in this case 9 minus 2 will be 7, and again it will not be greater than equals to your target. So just push 9, because 9 is maintaining the increasing order of the stack. I mean, it is not a stack, it is a DQ. It will maintain the monotonically increasing order. 9 can sit over 2 because 9 is greater than 2. Now you move to 3, add 3 to it, and this becomes 12. Now this value is greater than equals to your target. As soon as this happens, then you can compare it with the shortest window size. It is already integer max, and you can update it with the new window size, which is I plus 1, which is index 2 plus 1, and this will become 3. Okay. Now can we insert this sum 12 to the end? Yes, 12 is greater, so we can insert it at the end. 12 comma index is 2. Fine. Now we move on to the next element, which is minus 8, and this reduces the sum from 12 to 4. 12 minus 8 is 4. Now is 4 greater than your target? No. Can we insert 12 to the right of, can we insert this 4 to the right of 12? No, because then the graph will come down. It will not be monotonically increasing. So if you want to maintain a monotonically increasing curve, you have to remove this. Keep on removing the items unless you find an item which is less than 4. Otherwise your DQ is empty. So I'll remove this 12, I'll remove this 9, and 2 is actually less than 4. So I can insert this 4 now. Okay, so this will be 4 comma, what is the index? It is 3. Fine. Now we move on to the next element, which is 4. So if 4 is added, it becomes 8. Is 8 greater than your target? No, it is not. So can 8 be inserted here? Yes, because 8 is greater than the top element. So this is basically your front element, okay, or your back element, whatever you call. If you call it back, then this is front. So you insert 8 comma index is 4. Now you move on to the next element. This is 10, and this becomes 18, and this is greater than equals to your target. So obviously if you keep on adding from the beginning till this point, then this entire array sum will be 18, and this will be greater than equals to target, and the size is I plus 1, which is 6. 5 plus 1 is 6. Compare 6 with 3, but 3 is lower, so don't do anything. Now can we insert 18 here? Yes, you can always insert 18, right? So you can insert it at the end like this, or you may delay the insertion, you may do some other process. So if you insert it here, then try to compare it with the beginning one. So if I happen to remove the beginning one, like I have found a window with sum greater than equals to target. So the second thing is we want to compress from the left side. How do I compress it? You check with the last element. If I subtract 2 from 18, will my sum be still greater than equals to target? Yes, it will be. So just pop it out. Okay, so if you pop it out, the sum value will be 18 minus 2, which is 16. Still this is greater than equals to target. Can we remove this 4, 3? If we remove this 4, 3, then the cumulative sum till this point is 4. If we remove this, then the remaining sub-array will have sum 18 minus 4, which is 4. I mean 18 minus 4 is 14, which is greater than equals to target. So you can remove it. Okay, now the next element is 8. Can we remove this? So if I remove this, then the sum available with us with the sub-array from starting from index after 4 will be 18 minus 8, which is only 10. So if I happen to remove it, let's say we removed it, then the sum left with us will be 18 minus 8, which will be 10, and now it has fallen below our target. So we'll keep popping it up unless we fall below the target, and as soon as we fall below target, whatever was the last popped item, I will store it in my current popped item. Okay, that item will be the starting point of our window. So 4 will be the starting point of our window, and the current items index will be the end point. So this will be the window, and what will be the size? 5 minus 4 plus 1, which will be 2. So compare 2 with the shortest, and 2 is less, so it will be updated. Now you move your pointer and you have parsed all the elements. Now when you are done parsing all the elements, whatever is stored in your shortest will actually be the smallest window size where the sum is greater than equals to your target. If while parsing, throughout the parsing, your shortest did not change the value from integer max, it remained as integer max, then you have to return -1, saying that there is no window where the sum is greater than equals to target. Fine. Now in this case, if you see, each element can be inserted into the DQ once and can be popped out of the DQ once. But once an element is inserted and taken out, it will not be reinserted. So the total time complexity is order of n, and the space complexity for this is order of n due to the use of this DQ. Let us now look at the code. In this problem, we are given the nums array as well as the target value, which is k. So I will find the number of elements, and I have taken a DQ in the form of pair, which is basically your cumulative sum, comma your index value, current index. Now I have taken a long sum variable as well as the shortest, which will keep track of the shortest window with sum greater than equals to your k value. Now I will parse all the elements one by one. Whenever I see an element, I will add it to my cumulative sum, which is sum. As soon as my sum value is greater than equals to my target, I will update my shortest with the minimum value possible, already known shortest value, comma I plus 1. Because the current window till the ith index from the 0th index will be containing a sum value greater than equals to k, because the sum is greater than equals to k, right? And sum is being calculated from 0 index. Now once this is done, then we will try to compress the window size from left. Maybe compression is possible. Maybe we will remove the 0th element and still we will be taking from index 1 to index I, and again the sum will still be greater than equals to k. It might so happen, right? For that reason, we will keep on compressing unless the compression is not possible. Okay, so if we take out 0, we will check for the sum from 1 to I. Is it greater than equals to our k value? If it is, then I will also remove 1 and I will check from 2 to I. And I will keep on doing unless my sum value actually falls below k. Otherwise, my DQ is empty. Okay, so this is that condition. So this condition here checks if you have popped out any element. If you have compressed by any element, then the last popped item will be the starting index, and ith item will be the ending index of the current subarray, and you have to compare it with the shortest subarray already found and take the minimum of these two and store in the shortest. Okay, so you have to dry run this code in order to understand it properly. Now the last case was before pushing any item, let's say before pushing 10 over 8, we have to check if the top of the DQ, that means the front of the DQ, or you can say the back of the DQ, whatever. So we say back. So the back of the DQ should have a value less than the current item, and then only you can add 10 to the back. Otherwise, if it was, let's say, 18, then it will not be monotonically increasing, right? Then you have to pop out some items unless you find an item which is less than 10 in the back of the queue. Otherwise, your DQ is totally empty. Until then, you keep popping out the elements. This is that case. And after the suitable element is maintained or your queue is empty, then you can add your suitable value, which will actually maintain your graph in monotonically increasing order. Once the entire processing is done, if the shortest is never updated, it is integer max, then none of your windows actually have a sum greater than equals to k. So you will return -1. Otherwise, if this was updated at least once, then you will return what is the minimum window size with sum greater than equals to k. Okay, so this is the entire code, and in order to get a better understanding, you should do the dry run by taking some examples. So I hope you were able to understand it. If you want to join our DSA mentorship program, then you can contact us on WhatsApp to get more details, and we can guarantee that you will be interview ready in just 3 months. If you like this video, then please hit the like button and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.